Hey everybody, it's JB. We're back again talking about Newton's laws, and we're going to include in this circular motion. Someone did in fact send in a good deed, so I'm going to do a little freestyle rap about this right now. Let me just find a good beat here. Oh yeah, here we go. Yo, I heard a little story that I wanted to tell you. Robbie saved the day. That was swell, yo. He saw someone broke down in the middle of the street. He didn't miss a beat. He made it complete. He jumped out of his car. He saved the day. He helped the person. He made that day. I tell ya, ain't no better way to start out than doing what's right. That's what it's about, yo. All right, that's all I got for you. So keep on sending in those good deeds, and we'll do more of those freestyles. All right, so back to Newton's laws. And here we go. So Newton's laws, got a lot of cover here, and you will find these notes on your website homepage. They're all available for you to check out, and I'm just going to go over them right now. Starting off with the four fundamental forces. There are actually only four forces that we've established that exist. There probably are more. We don't know what's causing the universe to accelerate outward, so there may in fact be a fifth or more. But the four fundamental forces in order of strength, we start off with gravity, the weakest one of all, believe it or not. Then the weak force, which only happens inside the atom. The electromagnetic force, and the strong force. Strong force is the strongest of all. In fact, that's what holds the nucleus together, so it actually has to be stronger than the electromagnetic force so that it can keep those protons, which really want to get away from each other due to the electromagnetic force. It's got to keep those together. Now, classically, we divide forces into kind of two different categories. Classically, meaning before we knew about any of this stuff over here. We define them in, separate them into contact forces, which would be like a hand pushing a cart, your rope pulls a sled, or the force of friction, versus non-contact forces, stuff like the two charged particles. They will repel each other or attract each other depending on their charge. Magnetism, non-contact force, and of course two masses, any masses, will attract each other due to the force of gravity. Actually, all the forces are field forces. For example, when I push this pen right here, it's the electrons in my finger that are repelling the electrons in the outer shell of this thing. So that's a repulsive force. That's the electromagnetic force. Even friction is just the electromagnetic force because my fingerprints, all the ridges in my fingers, are getting caught between the little microscopic ridges on this, and that is how I pin this between two pressing forces. So even electromagnetism is or rather even friction is electromagnetism, the interaction of electrons in the outer shells of my fingers and this pen. Newton's laws only work in inertial frames. So inertial frames are frames in which there is no acceleration. In an accelerated frame, you may feel like force is being exerted on you, but they don't exist. For example, if you're on a merry-go-round, it may feel like you're being pushed to the outside, but you are really not. In the inertial frame of the Earth, you just want to continue at a constant velocity, but it feels to you like you're being pushed to the outside. You are not. If you just step off of a merry-go-round, you will not go outward, you will go tangentially. So there really is no centrifugal force on a merry-go-round. By the way, the Earth is only approximately inertial. Because of the rotation of the Earth, it's actually accelerating, but it's a very small acceleration. It's 0.04 or 0.03 meters per second squared. That's due to its rotation, and it's even smaller due to the revolution around the sun, 0.0044 meters per second squared. So we can essentially ignore those for the purposes of our labs and assume that the Earth is an inertial frame. Now, mass. What the heck is mass? Mass is inertia, resistance to acceleration. So it's measured in kilograms. Inertia, resistance to acceleration. That's different than weight. Mass is universal. No matter where you are on the planet or where you are in the universe, it's going to be just the same difficulty to accelerate this back and forth. So one way to do this is to put your elbow on the table and hold this up, and you don't have to exert any effort to hold it up. So gravity's being canceled out for you, so you don't have to worry about that. You just try to accelerate this back and forth, and you are experiencing the mass. Now, this would be on a different planet. Would this be any more difficult or any more hard to do this? No, it would be just as easy no matter what planet you're on. Lifting it up might be easier or harder depending if there's more gravity, but that's because you are exerting a force against the weight. The weight is, in fact, the force of gravity, and that depends on your location. Your weight is zero in deep space. On a space station, you may see astronauts floating around. They are not weightless because they're so far from the Earth. They're not weightless, but they're in free fall. If you're in an elevator and you're falling down, and you just let this pen go in the elevator, it'll fall down with you. So it looks, for all effect, it is weightless. There's no normal force pushing up on it. So that's why the astronauts in the space station are floating around, because they're in free fall. There actually is gravity. It's a fraction of g up where they are, but it's not zero.